40 light-years from Earth, there's a planet roughly the size of our own that orbits a small, violent red star, and scientists are trying to answer a question that could change our understanding of life itself. Its name is TRAPPIST-1e. It isn't a second Earth, not yet. We don't even know whether it has an atmosphere, but that's exactly what makes this world so fascinating. TRAPPIST-1e sits in the region around its star where temperatures could, under the right atmospheric conditions, allow liquid water to exist on the surface. And this isn't just another distant planet on an astronomer's catalog. It's one of the worlds that could help answer one of humanity's oldest questions. Are we alone? The system lies about 40 light-years away, meaning the light we receive today began its journey roughly 4 decades ago. And the strange thing is that this alien system is packed with worlds. 7 Earth-sized planets orbit the same red dwarf. 3, TRAPPIST-1e, F and G, are in the star's traditionally defined habitable zone. But TRAPPIST-1e is particularly interesting. Why? Because it's rocky, Earth-sized, and positioned where liquid water might be possible if the planet has the right atmosphere. So here's the mystery. If we could somehow stand there, would we see an alien ocean beneath an unfamiliar sky? Or would we find a cold, barren world stripped of the atmosphere needed for life? The James Webb Space Telescope is beginning to give scientists clues, and some of those clues are forcing researchers to rethink what habitable really means. Before TRAPPIST-1 became one of the most intriguing planetary systems in astronomy, scientists had a simpler way of thinking about habitability. Find a rocky planet, put it in the right temperature range, look for water, then ask whether life might be possible. But nature isn't that simple. The habitable zone is not a guarantee of life. It's simply a region where, under suitable atmospheric conditions, liquid water could exist on a planet's surface. Earth sits inside our sun's habitable zone. Venus is near the inner edge. Mars lies toward the outer region. Yet those 3 worlds have radically different environments. So being in the right orbital neighborhood isn't enough. And TRAPPIST-1 makes the problem even more complicated. Its host star isn't like our sun. It's an ultracool red dwarf, much smaller and cooler than the sun. That means the habitable zone is extremely close to the star. TRAPPIST-1e orbits its star in only about 6 Earth days. All 7 known planets orbit closer to their star than Mercury orbits our sun. That sounds terrifyingly close. And it creates another fascinating possibility. The planets are likely tidally locked. In other words, one side may permanently face the star while the other side remains in darkness. Imagine a world where the star never rises or sets. One hemisphere constantly receives stellar radiation. The other exists under perpetual night. Could such a planet still have a stable environment? Possibly. If an atmosphere exists, winds could transport heat around the planet. The exact climate, however, depends on factors scientists still don't know. And that's the key. We're not looking for an Earth copy. We're looking for evidence that nature can create environments capable of supporting conditions associated with life. If that blew your mind, hit like, because we're about to get to the part that makes this world much more complicated. When astronomers discovered the TRAPPIST-1 system in 2017, it immediately became extraordinary. 7 planets roughly comparable in size to Earth were found orbiting one star, and 3 of them appeared to occupy the habitable zone. But then the James Webb Space Telescope arrived. Webb was launched in December 2021 and began science operations in 2022. Its infrared instruments gave astronomers a new way to investigate the atmospheres of these tiny worlds. Here's how it works. When a planet passes in front of its star, some of the star's light travels through the planet's atmosphere, if an atmosphere exists. Different molecules absorb different wavelengths of light. So by measuring tiny changes in the spectrum, scientists can search for chemical fingerprints. It sounds simple. It isn't. The planet is incredibly far away. The star is much brighter, and the atmospheric signal is tiny. Then there's the star itself. TRAPPIST-1 is active, producing flares and star spots that can contaminate the measurements. So astronomers have to separate the signal from the planet from the much stronger signal coming from the star. Webb has already revealed important information about other members of the system. For TRAPPIST-1b, observations indicated a very hot day side and little evidence for a substantial atmosphere. TRAPPIST-1c also appears unlikely to possess a thick atmosphere. And in 2025, Webb observations of TRAPPIST-1d found no detected water, methane, or carbon dioxide signatures in the analyzed data. That was a warning. Being Earth-sized and near the habitable zone doesn't automatically make a planet Earth-like. So what about Planet E? That's where the mystery deepens. In September 2025, NASA reported initial Webb results from 4 observations of TRAPPIST-1e. And instead of delivering a simple answer, the data opened several possibilities. Researchers concluded that the planet almost certainly doesn't have the thick, primordial hydrogen and helium atmosphere it might have possessed when it formed. But that doesn't mean TRAPPIST-1e has no atmosphere. A planet can lose its original atmosphere and potentially develop another one later through geological and chemical processes. Earth itself isn't using the same atmosphere it had when the planet first formed. So TRAPPIST-1e could still have a secondary atmosphere. Or it could have a very thin atmosphere, or perhaps almost none at all. The current observations can't confidently distinguish every possibility, and that's an important scientific lesson. Sometimes the most exciting result isn't discovering an answer. It's narrowing down what the answer can be. Think about what that means. A planet 40 light-years away is being studied not by sending a probe there, but by analyzing tiny changes in infrared light. What would you expect to find if TRAPPIST-1e had an atmosphere? Would you expect oxygen, water vapor, carbon dioxide, or something completely unfamiliar? And if scientists eventually found a convincing combination of gases associated with biological activity, how would humanity react? For now, we aren't there. There is no confirmed evidence of life on TRAPPIST-1e. And Webb hasn't produced a definitive detection of an atmosphere on the planet. But the search has entered a new phase. We're no longer asking only whether a planet exists. We're beginning to ask what its air might be made of. Here's where the science becomes fascinating. Imagine TRAPPIST-1e with a substantial atmosphere. The planet is probably tidally locked, meaning the same hemisphere continually faces the star. At first, that sounds like a recipe for disaster. One side gets continuous starlight. The other gets continuous darkness. Wouldn't one side become unbearably hot while the other freezes? Not necessarily. An atmosphere changes everything. Air moves. Heat moves. If the atmosphere is sufficiently substantial, winds could transport energy from the day side toward the night side. The ocean, if one exists, could also help redistribute heat. That doesn't mean TRAPPIST-1e would be comfortable. It simply means the climate could be more complex than one side burning, one side frozen. And there's another issue: the star. Red dwarfs are long-lived, but their early lives can be active. Powerful stellar radiation can affect planetary atmospheres, especially for planets orbiting extremely close to their stars. TRAPPIST-1 is no exception. That's one reason scientists care so much about atmospheric measurements. An atmosphere isn't just something a planet wears. It's part of the planet's entire climate system. It controls how heat moves. It interacts with radiation. It can protect the surface. It can also change the chemistry available to potential life. And there's a fascinating possibility. Maybe the best place for life wouldn't be directly under the permanent daylight, or even in the deepest darkness. It could be somewhere along the transition between them. A region where the stellar illumination is moderate, but that's only a hypothesis. Without knowing the atmospheric pressure, composition, clouds, and circulation, scientists can't simply draw a map of TRAPPIST-1e and declare where life could exist. That's why the observations matter. We're trying to reconstruct an entire planetary environment from a microscopic fingerprint in starlight. And then came the twist. But then new data changed everything. Webb's early observations of TRAPPIST-1e didn't reveal the clean atmospheric fingerprint some people might have hoped for. Instead, the data showed just how difficult this experiment really is. The planet's signal is mixed with the activity of its star. Flares and star spots can alter the apparent spectrum, and because the planet is so small compared with its star, the atmospheric signature is incredibly subtle. The result? Scientists can't yet confidently say TRAPPIST-1e has an Earth-like atmosphere. But they also can't confidently say it's a barren rock. That uncertainty is scientifically valuable. NASA's current assessment is that TRAPPIST-1e's thick hydrogen-rich primary atmosphere is unlikely, but multiple possibilities for its present environment remain open. And this is where the story becomes bigger than one planet. Because scientists aren't simply trying to find another Earth. They're trying to understand whether Earth-like environments are common or extraordinarily rare. If planets around red dwarfs can retain atmospheres despite intense stellar activity, then the number of potentially habitable environments in the galaxy could be enormous. But if red dwarf radiation routinely strips atmospheres from close-orbiting rocky planets, the picture changes dramatically. Suddenly, the universe might contain billions of Earth-sized planets that look promising from a distance but are actually hostile. So which is it? We don't know yet. And that's why Webb observations of TRAPPIST-1e are so important. NASA notes that researchers will need additional observations, potentially many more transits over several years, to characterize these atmospheres with greater confidence. If you're enjoying this journey into one of the strangest planetary systems we've found, consider subscribing. The next observation could completely change the story. So let's step back and understand what scientists are actually measuring. They aren't seeing oceans. They aren't seeing continents. Webb can't simply photograph TRAPPIST-1e's surface and show us an alien landscape. Instead, astronomers measure light. When the planet crosses the face of its star, the star becomes minutely dimmer. That tells us the planet's size. But some of the starlight can pass through the planet's atmosphere. If certain molecules are present, they absorb particular wavelengths. The resulting spectrum becomes a kind of chemical fingerprint. It's incredibly powerful. But it's also incredibly difficult. Imagine trying to identify a thin layer of gas surrounding a tiny planet from 40 light-years away, while the planet is passing in front of a much brighter, active star. That's the challenge. And scientists have developed increasingly sophisticated ways to handle it. For TRAPPIST-1e, researchers compared Webb's observations with models of possible atmospheres. The current data don't rule out an atmosphere, but they do rule out a thick hydrogen-dominated one because the expected spectral features aren't present. That's an important distinction. Not detected doesn't automatically mean not there. It can mean the signal is too weak. Clouds can obscure atmospheric features. A thin atmosphere can produce a smaller signal. And stellar activity can complicate the interpretation. That's why repeated observations matter. Every additional transit gives researchers another piece of the puzzle. Eventually, the competing models should become easier to separate. And when that happens, we could learn whether this alien world has an atmosphere at all. If it does, the next question becomes even more exciting. What's inside it? Now imagine the implications if TRAPPIST-1e turns out to have a stable atmosphere and conditions compatible with liquid water. That wouldn't mean we've found aliens. It wouldn't even mean we've found life. But it would tell us something profound. It would demonstrate that rocky planets around small red stars can maintain environments that might be suitable for life. And that matters, because red dwarfs are extremely common stars. If potentially habitable rocky worlds can survive around them, the galaxy's inventory of possible habitats could be much larger than we once imagined. But there's another side to this. TRAPPIST-1e could also teach us that habitability is fragile. Perhaps its atmosphere is thin. Perhaps stellar activity has dramatically altered its chemistry. Perhaps the surface is dry. Perhaps water, if it exists, is trapped beneath ice. Or perhaps conditions are far more interesting than we currently expect. Every possibility changes the scientific question, and that's why the word habitable needs to be handled carefully. A habitable zone planet isn't necessarily habitable. A potentially habitable planet isn't necessarily inhabited. And an inhabited planet doesn't necessarily have an atmosphere that looks exactly like Earth's. Life elsewhere might operate under environmental conditions we've never encountered. That's one of the biggest reasons scientists are cautious about claiming biological discoveries. A single molecule isn't enough. Even a potentially interesting gas isn't enough. Scientists need multiple lines of evidence and must rule out non-biological explanations. TRAPPIST-1e hasn't reached that stage. But if future observations eventually revealed a convincing atmospheric combination that couldn't easily be explained by geology or chemistry alone, the consequences would be enormous. Humanity would have its first strong evidence that biology may exist beyond Earth. How would that change religion, philosophy, science, politics, or simply the way you look at the night sky? That's the question hiding behind this tiny red star. Maybe one day, observations of this system will reveal an atmosphere unlike anything we've ever studied. Maybe they'll reveal a world stripped bare by its star. Or perhaps, someday, scientists will find evidence that makes us confront the possibility we've wondered about for centuries, that life didn't begin only once. For now, there is no confirmed evidence of extraterrestrial life on TRAPPIST-1e. The mystery remains open. And maybe that's the most exciting part. Because somewhere around a faint red star, a world is completing another orbit, and its light is still traveling toward us. If this story changed the way you think about humanity's place in the universe, hit like and subscribe for more scientifically grounded cosmic discoveries. And drop your biggest question about TRAPPIST-1e in the comments.